Chapter 7, Section 5, Properties of Determinants. Determinant is a fundamental concept in linear algebra relating to square matrices. The determinant of a matrix provides important information about the matrix, such as whether it is invertible, the volume scaling factor of the linear transformation it represents, and more. Understanding determinants and their properties is crucial for solving systems of linear equations, finding inverses of matrices, and many other applications in mathematics. As we saw in the previous section, for a 2x2 matrix, we can compute the inverse matrix using the determinant and adjugate of the matrix. As an example, let's compute the inverse matrix of this matrix A. We can compute the inverse matrix of this matrix using this formula. The denominator is the determinant of matrix A. We can compute the determinant by this formula. This matrix is called adjugate, which is obtained by swapping the diagonal elements and changing the signs of the off-diagonal elements. In this section, let's focus on determinant. The determinant is a scalar value that can be computed from a square matrix. The determinant of matrix A can be denoted in this way. For a 2x2 matrix, the determinant can be expressed in this way. The determinant has several geometric and algebraic interpretations, but at its core, it is a measure of a matrix's ability to scale volume and the invertibility of a linear transformation. Specifically, for a square matrix A, the determinant is a single number that summarizes the following key properties of the matrix. The first is invertibility. A matrix is invertible only if its determinant is non-zero. The second is volume scaling. The absolute value of the determinant represents the factor by which the matrix scales volumes in the space it transforms. The third is orientation. The sign of the determinant indicates whether the transformation preserves or reverses the orientation of the space. We already know how to compute the determinant of a 2x2 matrix. For a 3x3 matrix, computing the determinant is slightly more complex. We can use the rule of Sarrus or cofactor expansion to compute the determinant of a 3x2 matrix. First, let's apply the rule of Sarrus. In this method, the determinant is calculated using the main diagonal and its extensions, plus the anti-diagonal and its extensions. Next, let's use cofactor expansion to find the determinant of the same matrix. This method is also called Laplace expansion. This method expands along a row or column using cofactors. A cofactor is the determinant of a smaller matrix obtained by deleting a specific row and column. As an example, let's use this 3x2 matrix to find its determinants. By applying the rules of Sarrus, we can obtain this result. And by applying cofactor expansion, we can obtain this result. As we can see, the two methods generate the same result. The details of cofactor expansion is provided in the next section. So, if you are new to this method, please watch the next video. So, what are the key differences between the rule of Sarrus and cofactor expansion? Regarding mechanisms, as we can see in the formulas, the rule of Sarrus relies on shortcut using diagonals. On the other hand, cofactor expansion used minor determinants and alternating signs. As to applicability, while the rules of Sarrus can be used only for 3x2 matrices, cofactor expansion works for n by n matrices for any size. This is a critical difference. As to ease of use, the rule of Sarrus can find the determinant of a 3x2 matrix quickly. Cofactor expansion is more versatile, but its computational cost can be high for large matrices. In sum, while both can be used for 3x3 matrices, while the rule of Sarrus is a shortcut specific to that case, cofactor expansion is a more general and versatile approach. Determinants have several important properties that are useful for calculations and understanding the nature of linear transformations. In the following, each of these properties will be explained one by one. First, the determinant of the identity matrix of any size is 1. The identity matrix represents a transformation that does nothing to the space, preserving both volume and orientation. Second, the determinant of a triangular matrix is the product of its diagonal entries. This property makes it easy to compute the determinants of triangular matrices. Third, the determinant of the product of two matrices is equal to the product of their determinants. Fourth, the determinant of a matrix and its transpose are the same. Regarding the row operations and determinants, the effect of elementary row operations on the determinant is as follows. Swapping two rows of a matrix multiplies the determinant by -1. Multiplying a row by a non-zero scalar multiplies the determinant by that scalar. Adding a multiple of one row to another row does not change the determinant. If a matrix A is invertible, the determinant of its inverse is the reciprocal of the determinant of A. Let's see the property regarding determinant and eigenvalues. For a square matrix A, the determinant is the product of its eigenvalues. This property is often used in spectral analysis and for understanding the behavior of linear transformations. We will see what eigenvalues are in later lectures. Finally, let me show you the property regarding scaling a matrix. If each element of a matrix A is multiplied by a scalar k, the determinant of the resulting matrix is k to the power of n times the determinant of k, where n is the size of the matrix. In this lecture, we explore the key properties of determinants, which play an important role in linear algebra and its applications. Understanding these properties not only provides mathematical insight, but also equips us to apply determinants in solving systems of equations, understanding transformation, and studying the stability of systems. Thank you for watching. Please thumbs up and subscribe to my channel.